Hi guys, and welcome back to another lesson. Today or now we are going to talk about determining file information. We're going to continue from this part and onwards. So obtaining information about files and devices. The OS module is heavily biased on the Unix way of doing things. As such, it treats devices and files similarly. So finding out about devices such as the current terminal session looks a lot like finding out about files. So in this section, we'll look at how we can determine file status and permissions, and even how to change some of their properties from within our programs. So let's write some code. First we have to change into our correct folder. So let's start Python and import the OS module. I'll explain in a minute what I'm doing. So here we check the current directory with the quote dot quote listing with the os.list. And now that we've seen os.list, we hopefully realize that we use that our use of ls or dir in subprocess was rather artificial, because os.list does the same thing directly from Python and does it more efficiently. We then use the os.stat function to get some information about one of the files. This function returns a name tuple object that contains 10 items of interest. Perhaps the most useful of these are the st underscore uid, st underscore size, and st underscore mtime. These values represent the file owner's user ID, the size, and the last modification date time. The times are integers that must be decoded using the time module. So we can do that as well. So if we try to access the mtime, I can type it correctly. So here we have the exact time of when the file was modified. This has to be put in correctly, otherwise So here we use the time module's local time function to convert the integer st underscore and time value into a time tuple showing the local time values, and from there into a readable date string using the time.strf time function with a suitable format string. We'll look more closely at the time module in our upcoming part of this lesson. The simple 10 value tuple return from os.stat is generally convenient, but more details are available via the os.stat than the tuple provides directly. Some of these additional values are OS dependent, such as the st underscore ob type attribute found on RISC OS systems. We need to do a little bit more work to dig this out, and we can access the details by using object attribute dot notation. Perhaps the most interesting field that we can access from the os.stat is the st underscore mode value, which tells us about the access permissions of the file. So let's start to try to work with that. But that's not too helpful. It's just an apparently random number. The secret lies in the individual bits making up the number. It's another bit mask. So the st mode is conceptually similar to the umask, but with the bit meanings reversed. So we can see how the access details are encoded by looking at the last 9 bits. By using the bin function in combination with the slice, we have extracted the binary representation of the last 9 bits. So looking at those 3 groups of 3, we can see the read, write, execute values of owner, group, and world respectively. So the higher order bits also have meanings, and the stat module contains a set of bit masks that can be used to extract the details on a bit-by-bit basis. For most purposes, the preceding access bits are sufficient, and helper functions exist in the os.path module that enable us to access that information. We have several other ways to determine access rights to a file in Python. In particular, the os module provides a convenience function, os.access, that takes a file name and flag variable that returns a Boolean result depending on whether the file exists or is readable, writable, executable, respectively. These functions are all easier to use than the underlying os.stat and bitmask approach, but it's useful to know where the functions are getting their data. And finally, the OS documentation points out a potential issue when checking for access before opening a file. there is a very short period between the two operations when the file could change either its access level or its content. So as is usual in Python, it's better to use try except to open the file and deal with failure if it happens. So we can then use access checks to determine the cause of failure if necessary. So let's just write some pseudocode to illustrate those checks. So we would write something like this. So this is the basic structure of the access checks. So having seen how to explore properties of individual files, we now look at the mechanisms available for traversing the file system, reading folders, copying, moving, and deleting files, and so on. So now we'll move over to navigating and manipulating the file system. So Python provides built-in functions for opening, reading, and writing individual files. The OS module adds functions to manipulate files as complete entities. For example, renaming, deleting, and creating links are all catered for. However, the OS module itself provides only half of the story when it comes to working with files. We look at the other half when we explore the shuttle module and other utility modules that worked alongside the OS module. One note is that in Python 3.4, a new module was introduced called pathlib, which aims to provide an object-oriented view of the file system. This potentially replaces much of that functionality discussed in this section. However, pathlib is marked as provisional, which means that the interface could change significantly in future releases, or the module could even be removed from the library. Because of the uncertainty, pathlib, we are not going to use pathlib here. So we start with reading and navigating the file system. We've already seen how we can use the os.listdir to get a directory listing and os.getCwd to tell us the name of the current working directory. We can use the os.mkdir to create a new directory and os.chdir to navigate into a different directory. I'll show you how to use all these functions that I'm talking about. So that is the current working directory. created a new directory. So after importing the OS in the first line, we stored the current directory in CWD and then printed it to confirm that we were where we thought we were. We then listed its contents. Next, we created a folder called subdir and changed into that folder. We've verified the move succeeded by calling the os.getCWD again from the new folder and found that the folder has indeed changed. Finally, we changed back up to the previous directory using the quote ... shortcut and once again verified that it worked with os.getCWD. And that quote ... is same as like cd and two dots to move back up one folder. So one problem with the os.mkdir function used here is that it can only create a directory in an existing directory. If we try creating a directory in a place that doesn't exist, it fails. Python provides an alternative function called os.makeDirs with a s in the at the end, but also spelling out instead of mk it uses the make word. So just note the difference in spelling that creates all the intermediate folders in a path if they do not exist already. So we can see how this works with the following commands. And it should be in quotes. It's supposed to fail, so I'm just not doing it right. There. And we can see in the our projects folder that there is no folder called test2. It has created. So this is the current working directory. So here the original os.makedir call produced an error. This one up, this is the error I'm talking about. This first I've just messed up. And it produced an error because the intermediate folder test2 did not exist. The call to os.makedir succeeded. However, creating both the test2 and the new testdir folder, and we were able to change into this new testdir to prove the point. Note that os.makedir raise an error if the target folder already exists. We can use a couple of additional parameters to further tune the behavior, but the default values are usually what we need. Another module, Shuttle, provides a set of higher level file manipulation commands. These include the ability to copy individual files, copy whole directory trees, delete directory trees, and move files or whole directory trees. One anomaly is that the ability to delete a single file or group of files. That is actually found in the OS module in the form of the os.remove function for files and os.rmdir for empty directories. Although shuttle.rm3 is more powerful and usually what we want. Another useful module is glob or glob. This module provides file name wildcard handlings. We are probably familiar with the question mark and the star wildcards used to specify groups of files in the OS commands. For example, star.exe file specifies all files ending in .exe, .glob does the same thing in order in our code by returning a list of the matching file names for a given pattern. So let's try using wildcards, copying, deleting, and moving files using the functions from OS, glob, or shuttle. So let me just clear this up. So this is the working directory. And we just need to create a let's just create a file which is called test.py. It's not important what's in there, we just need the file. This is everything in the folder. This is the same. This is ask for files with an extension. This one gets the test files only. text file starting with file string. Any file with a 2-letter extension. Now we'll use the shuttle functionality. Yep, created a copy of file A and named it to file X. Yep. I'll explain in a minute when I finish typing. I need to remove the test2 file tree. Now let's play a little bit more with the OS module. There it is. Empty. So I'll explain what I've been messing with here. So in the first set of commands, we compare the effect of os.listIr with various patterns in the glob function. The first pattern with the star quote replicated what os.listIr did by listing the full contents of the folder. And the second pattern, which is quote star quote, listed all files with an extension. Strictly speaking, glob does not know anything about files or folders. It works strictly with names, so it actually listed all names that had a period included regardless of what kind of object it was. Next, we use the quote star.txt quote pattern to find all the text files, followed by quote file ?.txt quote to find any txt file whose names starts with file followed by a single character. Finally, we use the combination of wildcards to find any file whose name ends in 2 characters with the quote star.?? and quote. The second set of commands looked at the shuttle file manipulation commands. We started by using shuttle.copy to copy single files, file a.txt to a new file in the same folder called file x.txt, and file b.txt to the subdirectory subdir with a new name file y.txt. We then used os.listIr twice to see the result in each folder. We next looked at directory level operations with the shuttle.copyTree function that copied the subdir directory and its contents to a new folder test3, creating it in the process. Again, we used os.listIr twice to confirm the results. We used shuttle.rm3 to delete the test2 folder and its contents. Once again os.listIr proves the point. So we started the next sequence by creating another folder, test4, using the os.makedir function. Into this new folder, we move the file y.txt using the sh.move function, again using os.listIr on both folders. Proves that the operation succeeded and the file no longer exists in subdir, but does exist in test4. And finally, we looked at removing files with os.remove function. The first example removed the file from test4 and verified that it had been deleted. The next line attempted to remove test4 itself, but produced an error because os.remove works only on files. If we need to remove a directory, we should use the shuttle.rm3 again, or you could have used the os.rmdir functions to do the same thing. And we finished off by using os.listIr once more to confirm that the folder had gone. So if you look at the shuttle documentation, we'll see several variations on the copy functions with subtly different behaviors. In most cases, standard shuttle.copy function does what you want. Other features of shuttle include the ability to create archived or compressed files in either zip or tar formats. Also, we can extend the functionality of several of the functions using optional arguments. One of the most interesting is the shuttle.copyTree function, which has an ignore parameter. We can set this to a function that takes 2 arguments, a root folder and a list of files. The function must accept 2 parameters even if they are not actually used by it. The function then returns another list of file names that shuttle.copyTree ignores. This function is then called by shuttle.copyTree for each folder of the tree being copied, with the argument being the current folder within the tree and the list of files produced by os.list_dir acting on that folder. This is useful for ignoring temporary or archive files or files that can be recreated later. So what I'm going to show you now, it's an example that copies a project directory tree but ignores any compiled Python files. In example, those with an extension of .pyc. So let's create our own function. Just move it a little bit down here. Typing. So these are just example names of imaginary files. So we already have some, do I have a PYC file? No, I don't have a PYC file here, so let me just create. We have some py files, so let's see if we can So it should have created a project back, yeah, and copied all of the files in the new folder, and ignoring the PYC files. I mistyped it here, so, but it ignored the 2 PYC and took the rest of the files with him. So this is, in this case, we use the list comprehension to build the ignore list, but we could equally just return a hard-coded file name. For example, RCS to avoid copying version control files across, or we could have a much more complex piece of logic involving database lookups or other complex processing. The scenario of testing for a standard pattern, like the quote star.pyc in our case, is so common that Shuttle has a helper function called shuttle.ignore patterns, which takes a list of glob style patterns and returns a function that can be used in shuttle.copyTree. So we'll just recreate the previous example, but using the shuttle.ignore patterns. So if we just delete this folder for the time being, everything in the current directory, So it does the same thing. It ignores the PYC files. Again, making this mistake, forgot to change it. So remember that the ignore function is called for every folder being copied. So if it is very complex, the copy tree operation could become quite resource intensive and slow. Finally, consider a submodule of OS called OS.Path. The OS.Path module contains several helpful tests and utility functions that can help us when using the higher level functions. And the most useful functions are for creating paths, deconstructing paths, expanding user details, testing for path existence, and obtaining some information about file properties. And you should start your exploration of the OS.Path by looking at some helpful test functions. We saw earlier how we can use the os.stat to extract information about a file. os.path provides some helper functions that get the more common features more easily. We can, for instance, determine the size of a file using os.path.getSize, the modification time using os.path.getMtime, and the creation time with the os.path.getCtime. We can also tell whether a name returned by os.listdir, for example, is a file or a directory using the os.path.isFile or os.path.isdir. We can even test for mount points and links if that is important to us. All of these functions take a name as an argument and return true or false. That's a bit easier when calling os.stat and then using a combination of indexing and bit masking to extract the details. The next thing that os.path helps with is processing paths. We can find the full path to our file using the os.path.abspath, that's absolute path. And if it's a link, the path to the real file with the os.path.realpath. Having obtained that path, we can break it into constituent parts. So Python considers a full file path like this. It has a drive, then the path to file, and then file name, and then the extension. So using os.path .split drive, we can read the drive letter if we are on Windows, otherwise it's empty. os.path.dirname finds the folder, and os.path.basename gets the file name including the extension. We can even get the folder path and file name in one go with the os.path split. Usually that's sufficient, but if necessary we can further split the file name into its extension and core name with os.path split text, in which case the extension includes the period. For example, myfile.exe returns myfile and .exe. We'll see this in a minute. Often after having inspected and worked with the various path components, we want to reassemble the path or even create one from scratch. os.path provides another convenience function for this called os.path.join, which takes the various elements and combines them into a single string using the current OSPath separator as defined in the constant os.sep. This is very important because path format is one area that varies considerably across operating systems. Since Mac OS X appeared based on a Unix kernel, things have been a little easier because Windows usually accepts the Unix style slash separator in addition to its native backslash style, but it is still safer to use the os.path.join to create file paths if we plan on running our script on multiple computer types. So let's see this operation in action on our test files and folders. So we just need to use this command. File A and file and like always, I'll explain at the end what I'm doing. You have the subdir, yes. You have the test. That's strange. Yeah, because it's empty, of course. Creation time. So what we did here, we started off by importing the modules we need and checking the contents of the current folder, just to check that we are where we expect us to be. And then we compared the size and creation time of file A txt and subdir file C txt, which was a copy of file A txt. And we can see the sizes are identical, but the creation times differs, as we expect. And finally, we looked at some path manipulation. We used the OS.path split to break the file b.txt path into the folder and file parts. We joined them back with os.path join, and then we split up the file name to get the core name and the extension. And notice the period is preserved and at the front of the extension. So that was it for this part, guys, and the next part will be about plumbing the directory tree and going into the depths of walking the directory tree of files and folders. So I'll see you in the next video.